Hello and welcome. In this video lesson, we're going to take a look at how we can improve the traditional Euler's method, and we'll look at two iterations of how this can be done. So one of the things that we've noticed is that Euler's method is extremely prone to error and compounding of error. And the reason for that is because when we use Euler's method, we're assuming rates of change are constant for some non-zero interval of time. And so even if that interval of time over which we're assuming a constant rate of change is really, really small, eventually all those little tiny errors will accumulate, even for small step sizes, and we will get inaccurate results in the long run. So then why do we really study it if we don't use Euler's method? And the reason is because Euler's method provides an intuition for what it is that we're about to do. So one of the major reasons for this is that we are assuming, again, a constant slope that changes more or less rapidly, which varies from function to function. One improvement we could make to this is to pick a slope, which is perhaps an average of two slopes. So rather than to use one slope and to assume that that's the best slope for the entire interval, let's pick two of them, and one at each end of our interval to cause us to diverge from the actual solution less rapidly as we increase t. So if, for example, we compute one slope and it's too high, and we compute a second slope but it's too low, then the average of them, in theory, should get us closer to the slope that's just right. This method, or improvement to Euler's method, is often referred to as improved Euler's method, or Hong's method. I am not so much familiar with this name for it, but I'm guessing this is the individual who modified this. I usually think about this as Runge-Kutta 2. Now, Runge and Kutta were two mathematicians who came up with what we'll study soon, which is Runge-Kutta 4, sort of the default numerical method that we will use for precision. Runge-Kutta 2 is just a name for it because in a moment we'll see that it uses two slopes. So instead of our method resulting in one slope, recall that the way we did it before is we said to get the next value of y, we're going to take the previous value of y and add to it, depending on how big our change in time is, multiplied by our current slope. So what we did was, when we looked at this graphically, we said, okay, so here's our starting value, and we'll plug that starting value into our differential equation, which is f of t comma y. So this was some point t0, y0. It doesn't have to be times 0, it's just that's the way I'm drawing it here. So what did we do? Well, in this case, we went ahead and we computed f of t naught, y naught. So that's just the slope, right? That gives us a slope. And then what we did is we assumed that for some period of time, we'll just say that here's t naught, here's t1. Now that doesn't have to be 1 unit. That could be half a unit or a quarter of the unit, but this distance between these 2 points is actually what we refer to as the step size, the delta t, how long we're going to assume that constant rate of change for. So let's just suppose that we calculated the slope and the slope looked like that. It was a positive slope. So we assume that that positive slope is constant for that full interval of time, and we'll use that to calculate our next ordered pair, which is the point t1, y1. So this change right here, this vertical change that we have here, that is calculated by taking the change in time. So to get y1, we had to take the change in time, we had to take y naught, we had to add to it the change in time multiplied by how much we expect the change to be. So multiplied by this slope. So if this slope were, let's say, as an example, 3, if this were 3, that would mean that for a 1 unit change in t, we would expect a 3 unit change in y. But if our step were only a half, then we would estimate this red part to actually be 1.5, because half of 3 would tell you that if this were only a half a unit right here, that we would only expect half the rate of change increase. So that this generalization, now if we replace 1 and 0 with k plus 1 and k respectively, then that sort of tells us how we get from t1 y1 to t2 y2. It's just always using the previous information to get the next value. But suppose that instead of having just one slope here, which is what we have, what we did is we just replaced that one slope with the average of two slopes. So notice that this parenthetical quantity is just the average of two slopes. Why the average? We'll explore this a little bit more, but it just sort of intuitively makes sense. Let's average two slopes together. Now we're not going to call it slope 1 and slope 2. We'll call it k1 and k2. For the sake of just entertaining this idea, let's suppose, and so this would be our general form for that, now that we replace slope 1 and slope 2 with k1 and k2. So the real question is, well, what should k1 and k2 be? We'll prove that this should be true soon, but let's suppose that our k1 is just going to be the same slope as it was previously. So here's the actual solution curve. Now, if you take the derivative of the solution function, you get the differential equation that you started with. And so if that's the case, we're going to use the slope at our t0 value. Notice that t0 in this example is not shown as having to start at the y-axis. It could be at any point. It doesn't really matter. Now, this tangent line, this slope, the slope of that tangent line is given to us by the differential equation by plugging in this ordered pair right here, which without confusion should be the point t0, y0. And so we calculated that slope there, and then what did we do? Well, with Euler's method, we assumed that that slope was constant for some period of time delta t. You'll see that this picture and the picture that I've drawn here are virtually identical in the sense that we started off in Euler's method by using the slope at that point, projecting that slope forward, multiplying it by its step size to ensure that we get the right change, and that's just delta t multiplied by the rate of change per 1 unit of time. That gives us this next point t1, y1. Well, let's just entertain this idea that k1 will be the slope at the previous point. And I'll put previous in parentheses, or in quotes, because what I mean by previous in this drawing is t0, y0. K2 will be the slope at Euler's, the standard Euler's method, next point. So imagine, so like in this case, for the drawing, we would say this would be the slope at t0, y0. So that would be f of t0, y0. And so as an example, and the second point in this drawing, or the second slope we would get, is this, the hypothetical slope at t1, y1. Now we're not going to actually going to use that as our final t1, y1 because that's what Euler's method did. We're just going to grab a slope here. Then we're going to take this point, plug it into our differential equation, get the slope there. We're going to then average them together. So our formula, yk plus 1, will be y sub k plus delta t times, well, k1 is just the slope at the previous k, so I'll write this at f of t sub k comma y sub k, and that's going to be the average of that slope and then the slope at the next point, which I'll just write as t sub k plus 1 comma y sub k plus 1. So all this means is that we just need to evaluate the differential equation at the next point. So if we were at t0 and t1, this would be f of t0 y0, and this would be f of t1 y1. But we're trying to make this as general as possible. And then we average those two slopes together. Okay, well this is all great, but it doesn't really give us an operable definition of how to calculate the next slope, right? We have to sort of think about how we obtain t1 and y1. Well, t1 is really just t0 scooted to the right over, or shifted over to the right by delta t units. So t1 is t0 plus delta t. Oh, perfect. So I've been able to rewrite t1 in terms of t0, which is known, and delta t, which is also known. Now I'm going to write this more generally. And more generally, we could write this as t1, or t sub k plus 1 equals t sub k plus delta t. Now for the y component, we know that to get y1, we have to take y0, and that's just this formula up here, plus our step size multiplied by how much change we expect per change in step size, or per 1 unit change rather. And again, we could do this generally just by replacing our subscripts as appropriate. Y sub k plus 1 is equal to y sub k plus delta t times f of t sub k y sub k. Great. So now I can actually replace the parameters in this equation here. I can say y sub k plus 1. I can rewrite the right-hand side with everything being in terms of k and not k plus 1. So y sub k plus delta t times, and in parentheses I'm just going to write k1 plus k2 over 2, where, and now we'll go ahead and define these guys. We'll just say where k1 is just, again, the slope at our previous point, f of tk yk, and where k2 is the slope at the point tk plus 1 yk plus 1. But now I can rewrite tk plus 1 and yk plus 1 in terms of tk and yk. And don't worry, this will make a lot more sense whenever we look at an example of it. So this will be, okay, t sub k plus 1. So t sub k plus 1 is t sub k plus delta t. Y sub k plus 1 is y sub k plus delta t times f of tk yk. Okay, that seems like a lot, but here we have that summarized of what we just did. And you'll notice this is exactly the same thing that we derived here. It's a lot of substitution. It's attention to detail. But based on the fact that we picked these two slopes, again, one of them is just the standard slope that we would have picked in Euler's method. The second slope is if we had calculated t1, y1 by using the standard Euler's method, but then used that t1, y1 and computed the slope from the differential equation, and then averaged those two slopes together, this method applies right here.